Okay, light is a very important wave. It's one example, right? Now, if light is a wave, then it should display or exhibit all of the properties that waves exhibit. In general, waves, they do things like reflect, they refract, and they diffract, and they interfere. Right? Those are the main properties of waves. So we've already seen how light can reflect and refract. For example, when light passes from air into another medium, we can use the change in velocity, we can use the ratio of velocities uh, to define this thing called the refractive index of the medium. So we saw that as an example. We've seen examples of light being reflected. We saw that the angle of incidence equals the angle of reflection. So now what we're going to look at is diffraction and interference. Because if light is a wave, then it does these things too. So here is diffraction. Remember how we saw that when we send a wave, such as a water wave, through a small little opening, a tiny slit, the wave spreads out. If a beam of light passes similarly through a narrow slit, which is close to the wavelength of the light, then the beam of light also will spread out. Okay? So here's a slit. Imagine that we produce this slit. There's a wall here, and we cut out a tiny little hole, about 500 nanometers, and we send light through. Now, just a comment. In the real world, when we do experiments like this in physics, we use crystalline structures to produce these really tiny slits through which we pass light. So we use the crystal structures of certain compounds. Okay, so we're sending light through, and this is a ray or a beam, right? We call it a ray in physics, which means there are wave fronts, which are perpendicular to the ray, coming along as the ray moves forward. They finally hit the slit, and there's this semicircle kind of spreading out, which occurs just like that. So don't put this diagram anywhere in your notes. There's another diagram on the second page that I want you to put into your notes. Okay? So we could draw the rays of the resulting spread out wave, and they would look like this. They'd be perpendicular at every point, right, to the wavefronts that they pass through. And when these rays spread out like radii, like they sort of do in this example, we say that the rays are radial. They won't always be perfectly radial like this, because there won't always be a perfect semicircle formed by the spread out wave. This is kind of just what it looks like in the notes. It doesn't always look that way. Waves, okay, so that was diffraction. Now let's see interference. Waves do interfere, but only if they have the same frequency and similar amplitude. So the best way to see interference is through diffraction, through this. But instead of diffracting just through a single slit, we're going to place a second slit and have two of these semicircle patterns so that we can see clear overlap and clear canceling out of the waves. So imagine we take a light source, right? We pass a single beam through identical side-by-side slits, through two slits, side by side. That creates two identical wave sources which spread out like circular waves. Whenever two waves are identical, we call them coherent. That's the technical term. Oops. So when these waves from the two identical or coherent sources overlap, there are areas of brightness and darkness, that should be brightness and darkness, which are created where we have, due to things like constructive interference, destructive interference, canceling out because of the waves being out of phase. Right? So the resulting pattern of light could be viewed on a screen. If we actually did this experiment and sent a beam of light through two side-by-side slits, and then we put a screen somewhere away after the slits, after the light has had enough time to pass through the slits, spread out, and diffract and overlap, They would then reach the screen, produce this pattern of darkness and brightness, which would show exactly where we had had canceling out of the waves and where we had the waves in phase. And that pattern of brightness and bright spots and dark spots is called a diffraction pattern. So here we go. This is the normal scenario we know. The wave hits and it diffracts like that. But whoops, oh, now imagine, got ahead of myself. Now imagine we're going to put a second slit right here. Okay? What happens as the waves hit the slit? Well, when they hit the first slit, when these wavefronts hit the first slit, we see exactly what has been shown. That's what's produced. When they hit the second slit, there is a similar pattern produced, a similar circular wave produced at this point source. And so then there's overlap wherever two crests are on top of each other or intersecting. That means that we have positive, constructive interference. There will also be overlap of a crest and a trough. It spots like this. Where's my mouse? It spots like this right here. Oops. Right, we'll see overlap there as well. And wherever we have a crest meeting a trough, there will be cancellation of the waves, and it'll be perfectly dark. So here it is. I'm going to show it again with the two side-by-side slits producing the circular waves at the same time. It comes forward, the crests, they hit, and then these semicircles spread out, the crests spread out at the same time. So if we put a screen right here, eventually these overlapping circular waves, light waves, would hit the screen, and then we would see this pattern of light spots and dark spots. And that pattern, which we would produce on the screen, on the flat screen, that pattern would be called a diffraction pattern. So another property of waves is that we can polarize transverse waves, right? And in fact, we can polarize light. So the fact that we can polarize light suggests two things. One, light is a wave because waves are polarized. But it suggests really that light is a transverse wave, because only transverse waves can be polarized. So when light passes through Polaroid sunglasses, it becomes polarized in one direction. And we can test that this is true. Here's how you do it. You take a second piece of Polaroid, right? Or just a regular kind of piece of Polaroid, loosely hanging, not positioned inside of sunglasses, and you rotate it in front of the sunglasses. So as you rotate the piece of Polaroid in front of the glasses, what you find is that the polarized light leaving the Polaroid, the piece, it can only pass completely through the sunglasses when the Polaroid piece is in the exact same orientation as the sunglasses. If the sunglasses were not polarized, then it wouldn't matter what angle you had rotated the Polaroid filter, the piece of Polaroid, because the sunglasses would be unpolarized, and every single polarization coming from that rotating Polaroid filter would make it through the sunglasses. So we'll discuss this a little bit in a little bit more detail in class. Light is a wave. That means it has wavelength and amplitude. Specifically, light is an electromagnetic wave. That means that light is the propagation of an electric and magnetic field together. The fields oscillate, and that's what the oscillation is in an electromagnetic wave. These fields, the electric and magnetic fields, they always point perpendicular to the direction in which light travels. They also happen to point perpendicular to each other. So the direction of motion, the electric field, and the magnetic field, they form XYZ axes, right? They point all in perpendicular directions to each other. Because electric and magnetic fields are perpendicular to the direction of motion, that makes light a transverse wave. Light is not a mechanical wave, right? It does not require a physical medium to be transmitted. In fact, it can be transmitted through a vacuum just like space. This is not true of mechanical waves like sound. Sound cannot be transmitted through a vacuum, so if someone tries to talk to you in space, well, that would be problematic because there's no oxygen in space. But if someone were to try and make a noise in space, it would not be audible to anybody else because there's no medium through which a disturbance could travel. With all waves, as with all waves, light has wavelength and amplitude. Visible light occupies a specific wavelength range, which is from 400 nanometers to 800 nanometers. It just so happens that our eyes only detect that range of light. Different colors have different wavelengths. The Roy G. Biv that we all know gives the progression from highest wavelength, right, 800, that's red, to the lowest wavelength, violet, which is 400. Violet is the highest frequency and the lowest wavelength. Right? Red is the lowest frequency and highest wavelength. So in fact, violet is much higher energy than red light. Violet light has higher frequency, which means the frequency is much more, the wave is much more scrunched together, right? Lower, smaller wavelengths, so it's scrunched together. And that means it has more energy than the red light. So white light is simply all the colors of the visible spectrum mixed together in even proportion or fairly even proportion. If white light passes through a prism, the different colors are split up and they form a spectrum. So the reason this happens is because the angle of refraction depends on the wavelength, as it turns out. We didn't study this, but if different wavelengths of light hit the same, pass through the same medium, then they will refract at different angles. So different wavelengths refract by different amounts, and therefore the different wavelengths are refracted at different angles. When we see a rainbow in the sky, the same thing is happening, and all the tiny little water droplets in the sky are acting collectively as the prism. So they refract the light, producing the different colors which then pass to our eyes, causing us to see the rainbow. Visible light is just one very small sliver of the complete electromagnetic spectrum. The full range of wavelengths is from 10 to the negative 4 meters to 10 to the 4. And from across this full range, we actually we cover a lot of different categories. So not next class, because I didn't announce it, but the following class, we will have a quiz on these different categories. You have to know the names, X-ray, gamma, so forth. And you also have to know each category or each type of electromagnetic radiation. You have to know each of their wavelength ranges. So what about amplitude? We just talked about frequency. What about amplitude? The square of the amplitude is proportional to the intensity of light. And intensity determines how bright we perceive light to be. So we're going to talk a little bit about sound. If you shout in front of a cliff, the sound echoes back, right? Any wall is a good reflector of sound. So when you talk in a room, your voice reflects off the walls. And this is why you actually can sound different outside compared to in a room, because outside you don't have that reflection. When sound passes from warm air into cold air, it refracts. So we're going to see why this makes it easier to hear someone from far away on a still night. Basically what happens is that one pathway the sound follows is directly to you, but then some of the sound is going up into the air. Because it goes up from warm air into cold air, it refracts back down, so there's a second pathway traveling to the person, the listener. So you actually get two pathways of the sound rather than just one, and that amplifies the volume. Okay, so because sound is such a good reflector, it's really hard to do experiments where you actually produce or witness diffraction and interference. But we will look at some setups that, in theory, should allow for experiments to be conducted. We'll see those in class. Now, because I'm running out of time, copy these down, pause the video as you go, and get the notes on each slide. We will look at all of this in class in detail next time.